Okay, good morning, everyone. This is welcome to this morning's Research Bites with Dr. Ajay Menon, and welcome, Ajay, and thank you for doing it this morning. So Ajay is originally from Mumbai. He completed a PhD in environmental engineering at the Nanyang Technical University in Singapore, and is currently a postdoctoral fellow working with Professor Jin Ling on the separation platform of bioeconomy. Ajay is also the co-leader of the WAVA project under the SFI Future Innovator Prize, and he has been selected for the penultimate seed funding phase, which is a great achievement, and well done, Ajay, on that. So Ajay has strong background in entrepreneurship, having been the entrepreneur in residence at the Venture Centre National Chemical Laboratories in Pune in India before coming to UCD. He was also the co-founder and MD of Sequest Biosolutions, a Bangalore-based startup aimed at creating Internet of Things and algal photobioreactor-based solutions for improving indoor air quality. And this morning, he's going to talk to us about anaerobic digestion and how we can solve some of the circular bioeconomy challenges. Thanks, Ajay.
Yeah. Thanks for that, Geraldine. So hello everyone. Hope you're all doing well. It's going to be the last research bites session before the semester break. So hopefully it'll be light and everyone will have fun. I hope everyone can see my screen clearly. I'll be talking about using anaerobic digestion to drive circular bioeconomy solutions. So I'll briefly talk about the two terms that I used over here, circular bioeconomy and anaerobic digestion. Now, the economy that as it exists now is linear. We know the model. It's take a resource, turn it into a commodity, use it, and then dispose it. Now, we know that this is not a sustainable model. Additionally, it's increasingly dependent on complex international supply chains. The last year with COVID and with the Suez Canal crisis, it's shown us how fragile all these supply chains are. The emerging idea is circularizing this economy, so transforming wastes and side streams at every stage and putting them back into the economy using sustainable, smaller local supply chains, which they just don't make everything a little bit simpler, a little bit more sustainable, but they also boost the economy and the economic security of countries. However, this involves the creation of new supply networks, new value extraction processes. It might also cause some disruptions of existing processes, which is why establishing something like this is a bit challenging. Now, the bioeconomy with its biomass-dependent pathway is especially well suited for circularization, as over here, at every stage, the waste of one process is almost always the food, for another process. Anaerobic digestion now, on the surface, is a very simple process. You basically use a community of bacteria that work that work in the absence of oxygen. You can put in complex organic matter of any kind into the system, and it'll break it down to smaller molecules, to acetic acid mainly, and that is converted into methane and carbon dioxide combined with that's called biogas. It can be used as a fuel for burning, for electricity generation, and so on. Now, this is it has been established for a very long time. The first ever anaerobic digester-based biogas plant was actually made in Mumbai, not very far from where I was born and raised, more than 100 years ago. Now, this is the absolute simplest design. It's something that you'll find in any Indian school book. It's a tank underground where you can put in manure or any kind of organic waste from farms. It is digested by this anaerobic community, and you get biogas, which is generally used for cooking or for very low scale electricity or lighting purposes. And then you get a bit of fertilizer which you can use in farms. Now, this is called the Deen Bandhu model. It literally means friend of the helpless. Now, as you can imagine, this was very ideologically, it was very attractive for Gandhians in India as well as post-revolution China, where village or small rural communities could use the few resources that they had and convert it into energy and into fertilizer for the farm. So it's a very small circular economy before that concept was even talked about. Now, modern AD facilities are a bit more complex than this, but the central idea is still more or less the same. Now, around the 90s, uh, Europe kind of discovered that this doesn't just make ideological sense; it makes a lot of economic sense as well. And you saw a lot of AD plans being established, mostly in Germany, but in other parts of Europe as well. There's almost an exponential rise in both the installed capacity and the number of AD plants. And increasingly, the number of the AD plants themselves have large individual capacities as well. So it's not just decentralized; it's very centralized, highly planned stuff. Now, AD, the use of AD has been growing worldwide. It's mostly fueled by Europe and mostly Germany. So almost half the installed AD capacity in Europe and a third of the world is in Germany, but the rest of the world is catching up as well, mostly Italy, UK, some Northern European countries, as well as, China is always there. Now, AD and biogas makes a lot of good sense just in terms of economy. Biogas is a good fuel. It's an energy carrier. Like fossil fuels, you can store it, you can transport it, you can compress it in the area of waste doesn't add to the carbon dioxide load, because the carbon dioxide that you'll get from combusting the methane that would have been released as carbon dioxide in the form of decomposition anyway. It can be used for heat and electricity production. You can upgrade the biogas, that is, you can separate the methane out and then use it as vehicle. And also, anaerobic digestion can be used as to treat water before it is let out into rivers or ponds or other water sources. Now, this is how AD is used currently. The issue with this is it still fits into the linear economy system. It just acts as the last step in this whole cascading biomass system. But what we can do with AD is actually use it, as a centerpiece of a circular economy system. Now, there's a lot of ways in which you can use AD. You can use it as a manure co-digestion, the simple process that I talked about right at the beginning. You can use it to create fertilizer. It can be used as energy or income security for rural areas. You can use it to reduce odors from animal slurries. Biogas itself can be a raw material, as in the methane, yeah, it's a fuel, but if you separate the carbon dioxide out, it can be used in horticulture. It can be used for for CO2 driven processes. It can be used as a scavenger of organic waste streams. What I mean by that is, at every point in the food chain, you can get the organic waste streams out, put it into an anaerobic digester and get new valuable materials out of it. That's where, oh, I'm sorry. So that's a list of what I was just talking about. And you can create basically biorefineries based around this whole AD idea. Now, this is an example of this kind of a process put in motion. This is called the Magic Factory. It's a establishment in southern Norway, where instead of putting the anaerobic digestion part right at the end of a process, they have made it the centerpiece of their whole this small model agricultural farm, where everything from the food waste from the dinner table, your green waste, manure, and so on and so forth goes into. Just turn on the laser pointer. It goes towards the central anaerobic digestion facility. You get biofertilizer out of it that goes back into the food production. You get fuel for running vehicles, and they have actually turned it into kind of a tourist center, an educational place. So yeah, this is what can be done in on a larger scale as well. It's very scalable. You can do it in a decentralized day. You can do it as a decentralized thing. You can have it. You can have large facilities powering entire cities or communities. Now, sorry. Geraldine just did a very nice introduction, so I don't have to go into it. I'll just talk about my research focus and my what I would like to do in this in this whole sector. I'll use the last two publications that I have as a way of illustrating it. So the first one was. This is a review article that I published with Prof. Ling earlier this year, where we talked about how you can use AD as a suite of processes, not just a way of converting wastes into biogas. In fact, it might be more economically kind of more profitable, even more feasible to take it away from biogas production towards the production of high value fatty acids. Now, this is the process that I'd shown right in my first slide. Uh, this first part of the picture is your conventional AD process, where complex organic substrates are turned into monomers. These are then turned into acids, particularly acetic acid, and then methane producing bacteria take up the acetic acid and convert it into hydrogen, into carbon dioxide, and into methane. Now, what we proposed over here is, instead of letting the process go towards methane, it might be more interesting, it might be more profitable, it might make more economic sense to kind of short circuit the process over here, add some ethanol or lactic acid from other waste streams, and turn this process into something that produces C6, C8, C10, C5 acids, which are very valuable chemical ingredients that go into food products, into perfumes. They can be also used as precursors for making palm oil substitutes, which are way more sustainable than the actual palm oil that is used as an ingredient in so many industrial processes. The other idea, sorry. So I was talking about, producing this acetic acid and other fatty acids and methane and so on. Now, all this is done by a very complex consortia of microorganisms, mostly bacteria and archaea. So you have two groups in an AD reactor. Most of the species that you'll find over there are bacteria. Some of them are archaea. Now, bacteria do all these. They take part in the metabolic processes that produce that break down the substrates, that produce all the various acids that I showed in the previous graphic, that do that get rid of a lot of inhibitory products, that get rid of stuff that it's not it keeps the process from being unstable and so on. And then finally, you have two major archaeal species that take in the products that are produced from these bacterial communities, and they convert it into methane, which is the final product of this whole anaerobic digestion process. Now, the other idea that I have, that I like working on, is using this whole community as kind of changing it and poking it a little bit, and driving it towards the processes, just changing the composition of the community and driving it towards processes that we want, or driving it away from the processes that we don't want. Now, the issue is, generally, this anaerobic AD community is seen almost as a black box, where you put something in, you get something out. In my last publication, now this was literally just accepted on Saturday, so I don't have a nice picture of the actual paper. So over here, what we had done was we broke up the AD process into two phases. In one phase, you had all the hydrolysis and the acid generation, and in another phase, you took the products of that first phase, you fed it to methanogens and created methane. Now, what we saw over here is something that you see very regularly in AD processes, where after over a period of time, the productivity goes down, the process becomes a little more acidic, and that eventually leads to instability towards, the productivity going down. It can even lead to reactor failure. Now, looking at the issues, what we diagnosed was that this might be due to the lack of a few trace elements or micronutrients, as we call it, and uh, we narrowed the deficient elements down to just four. That was calcium, magnesium, nickel, and cobalt. And using surface response surface analysis and other optimization methods, we came up with a micronutrient cocktail of sorts that we fed into the reactor. And what we saw was almost immediate increase in the actual productivity of the process, as well as the stability in terms of the pH and the oxidoreductive potential and so on. So what we did was we were able to optimize the process a lot. And we carried out some next-gen sequencing to see what actually happened on the community scale over here. So this was the community right at this point before the addition of the micronutrients, when the process wasn't very productive. It was mostly dominated by just one species of thermatogae. These are generally involved in breaking everything down to the to smaller compounds and producing some acetic acid, some hydrogen, which can be taken up by the methane producing bacteria for the production of methane. Now, what happened after we added all these micronutrients was we really increased the diversity of the bacteria of the bacterial groups in the community, and we added not just to the functional diversity but also to the functional redundancy. Now both those things made the process not just more stable. They added groups that took out xenobiotic organic compounds that might be inhibitory to the methanogens. They added some extra hydrogen producers, or groups that would remove the excess acetate and other acids that would inhibit methane production. And the added diversity and the added redundancy of all these new bacterial species made the process more stable, and as I said, it made the process a lot more productive. So that is how I see AD being improved, uh, the process itself being improved and being made more useful in terms of the circular bioeconomy, uh, by having it by converting it from just something that you can tag on at the end of the process to something that you can use for creation of more value at every point in the chain. Now, let me just uh, over here in where after I joined UCD, my main work has been looking into the pre-treatment of biomass by pulse electric fields. Now, what pulse electric fields are is you use very high strength pulses of electricity. You pass them through the substrate, and that breaks up the substrate and makes it more bioavailable to the entire anaerobic digestion community that I've been talking about. And the first part of the whole process, the hydrolysis and the acid production, that is the rate limiting step of the process. If you speed this up, then your whole process becomes a lot more, the rate of production goes up a lot, and then you can play around with the actual anaerobic digestion process in terms of modifying the community or driving it towards other metabolic pathways. So what we have been doing in with Prof Link's group is come up with various PEF treatment regimes which are sustainable, which are green in the sense they use very little energy compared to conventional processes. They take very almost they cut down the time of treatment by almost a magnitude, and we were able to come up with three kind of regimes that showed complete solubilization of the substrate that we're looking at, that spent mushroom compost. So what we showed was just this one process itself can get the substrate solubilized almost entirely within 4 days. That would eliminate some energy intensive steps that go before anaerobic digestion of wastes, like maceration, grinding, and so on. What you could do is just put your substrate in, have the pulse electric treatment carry out the breaking down and increasing the bioavailability. And what we showed was all these regimes that we came up with, they increased biogas production from spent mushroom compost by almost double compared to the control. They reduced the actual process time, and they just vastly increased the productivity. So the maximum productivity reported in literature was 360 liters per kg. That's after all the kind of treatments that you put that are put into optimizing the AD process. Over here, with just one kind of treatment, we were almost able to match it. So let me just zoom out a little bit and talk about the big picture. So yeah, there's a lot of things that can be done with AD. AD looks like a great process, but the actual installed capacity of AD is still very very small fraction of the actual potential of AD, of biogas production, and so on. So this is due to a large number of reasons. AD plants need a lot of they're very capital intensive. Location is a problem. You have to put them where they make the best sense in terms of the supply chain, but you don't want to put them near places where people live and so on. The suitability of the substrates is a problem. You have at the end of the AD process, you get a lot of effluent and digestion, which then needs to be processed before it can be actually put to use or just disposed. Finding markets for a lot of the products that can be produced from AD, it can be an issue. And then, of course, the whole economics of the process needs to make sense. Uh, so AD is a solution, but it needs an ecosystem. The kind of comparison that I like to think applies over here is electric motors, electric vehicles actually. So just indulge me for a minute now. The idea of electric vehicles has been around for a very long time. GM had an electric vehicle out in '96. It was a very good car, but it didn't see a lot of sales. And in 2003, GM decided that there's no market for electric vehicles. They shut down this idea, and they got out of the EV business. In the same year, Tesla was founded. This was the first production car. It wasn't even a car. It was a Lotus Elise that they put their drive chain into. But what they did was they didn't just focus on the solution. They created an entire ecosystem around their car with the superchargers, their apps, self-driving, and so on. Once the electric car was put into this kind of into this kind of an ecosystem, the solution transformed the entire segment. It has now become the standard. Tesla has its valuation is more than all these other big companies, big car companies combined, and now companies, everyone are scrambling to turn their entire fleets electric. So the solution was always there. It just needed the right ecosystem. And I feel this is the case with anaerobic digestion as well. And that was the thinking behind the WAWA project. that we created for the food challenge in SFI. The idea over here is bring together various technologies to valorize food waste and turn it into value-added commodities. So I'm a co-leader in this, but the lead is Dr. Saha from LIT. There's a combined effort from UCD, from LIT, from the private sector, and bioeconomy as well. So let me just go through the idea of this process. So we have food waste. It will be invariably created because of the whole food of the whole food to fork system. Now we have AD as a solution. We have horticulture as a solution. Horticulture is a nice way to produce, have a high productive, low resource intensive farming. And there's an emerging solution called microalgal photobioreactors, which is kind of using microalgae for food production. Again, it requires a very small parts of. It doesn't. It isn't that resource intensive, and it's seen as a future kind of future food, future way of solving the food crisis. Now, all of these solutions have their own problems. I've talked about the problems of anaerobic digestion. Horticulture has a growth medium crisis with with microalgal photobioreactors. You need costly nutrients. You need carbon dioxide to be pumped in. You also need a lot of post processing and so on. The main issue, however, with all these solutions is that they don't have the right ecosystem. They are kind of disconnected and they work in isolation. Now that is what we aim to solve with VAVA. We are aiming to convert these individual disadvantages into a solution for the whole process. The primary technology is going to be novel electroprocessing, so the PEF and the MEF that I was talking about. The pre-processing will efficiently and rapidly convert the mixed food waste from food producers to a high value consistent feedstock that can be sent to existing biogas plants or to decentralized plants as well. The same process can then be used to post-process the waste sludge and cost-effectively render it safe for reuse. A portion will be converted into growth medium for horticulture. The biogas will be sent to micro turbines that will convert it into electricity for the power grid. The CO2 from the micro turbines will be collected, as well as the liquid portion from the post-process sludge, and that will be used to harvest algal biomass, which will lead carbohydrates, proteins, and other nutrients, which will be separated from which will be separated using cascade separation and then put back into the whole bioeconomy. So this, as Geraldine mentioned earlier, this is a part of the future innovator prize by SFI. Now, this is a kind of a venture venture capitalism kind of based concept. It's not like a regular research grant. So it's a challenge based program where you have different phases, the application concept and so on. So we are right now at the seed phase. We have developed our concept and we are now trying to validate it, develop the team, carry out stakeholder engagement, produce a prototype, and so on. The focus over here is continued validation. So a lot of engagement with stakeholders, talking to them about the solution, creating, getting their feedback on what we are doing, and so on. So it's a very design thinking based process, and so yeah, that's hopefully what we're doing. The team is, like I said, it's a collaboration between LIT and UCD, and we the central part of over here is the private collaboration with FSM. FSM is Food Surplus Management. Is the biggest company that takes in food waste from various producers and right now they convert it into a soup and then send it to anaerobic digesters. Uh, Hopefully, Wawa will use these networks and improve uh, on their business model and come up with a solution that helps the whole bioeconomy and helps AD and uh, horticulture and algal food production as well. So on the UCB side of things, we have a team that is mostly James Link's group over here. Professor Nigel Brunton is a part of it as well. And on LIT will be focusing on the algal photobioreactor production side. We also have Bioorbic and Shannon ABC will be playing important roles in carrying out this whole project as well. Uh, so we have a lot of partners and collaborations to bring about this whole solution. The first is Prof. Ling Brunton and Elliot Kingston, who are here at Food and Health and Agriculture. This is where we'll be validating the actual technologies. The second is food surplus management. They'll be working with us to upgrade the food waste to a high value food, feedstock. The third is pure world energy. These are micro turbine. They are in the micro turbine business. They'll be helping us with the whole supply chain and the technology between converting the biogas into power and then harvesting the carbon dioxide. I'll be carrying out a collaboration with Dr. Khan from Chemical and Bioprocess Engineering as well for the process modeling and the economic analysis. Then with Prof. Nick Holden at Biosystems and Food Engineering for carrying out a life cycle analysis, the whole thing. That will be basically for to show that this whole thing actually makes sense in terms of sustainability. I'll be working with Prof. Meev Henchen at Chigas as well to develop a value chain, look at the supply, if making a supply chain that makes economic sense, and then creating a rural business model around this. We're still looking for more collaborations. We need to still work on the route to market for all the products that we'll be producing as in this whole Wawa process. Maybe look at GIS to identify the kind of the farms and the food producers that can be involved in this whole network of processes that we are building. Carrying out some omics research, the kind of research that I was talking about earlier, looking at the community and the metabolic pathways and so on. And then keep on carrying out stakeholder discovery, talking with people who are who are already in this sector, validating our process, talking with them to see if what we are doing makes sense, what kind of solutions they are looking for, what problems do they have, and so on. So yeah, sorry for taking so much time. This is uh, 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 the work that I've been doing and the work that we are still doing. If you want to, if you're interested in collaborations, we are open for it. If you just want to give me any of your inputs, or just talk to me about, if you want more information about Wawa, please email me. I'm on Twitter. Wawa itself has a website. It has a Twitter account. So if you want to engage, that's you can do it on those platforms as well. And yeah, that's it.
That's great.